Compare and contrast graphs of functions, y equals f of x, y equals f of 2 of x, all the way up to y equals f of k times x, where k is greater than 1. This is part of the family of functions series. We're going to investigate the absolute value function, compare and contrast these 6 graphs. If you have TI-Nspire technology, either a handheld, software, or an iPad app, we strongly urge you to play with the technology and discover some patterns when graphing. This is the TNS file that you could use, but if you don't have TI-Nspire, don't worry about it. We'll show this file during the video. All right, so here's the graph of y equals f of x, which is the absolute value of x. We have a slider over here using the letter k. The red is going to be the parent function. So when I click on the slider and increase k to 2, this is the graph of y equals absolute 2x compared to the parent function in red. Then k equals 3, 4, 5, and 6. And you'll notice what is happening there. Okay, I'm going to go backwards so you can see that one more time. So this is y equals absolute x, y equals absolute 2x, absolute 3x, and so on. As the value of k increased, what did you notice happening to the graph? Press pause as needed. One possible answer is the shape of the absolute value v gets narrower as the value of k increases. Let's go ahead and look at the graph side by side. Here is a graph of y equals absolute x, absolute 2x, 3x, and 4x. What we'd like you to do is list the domain and range of the graphs as they appear in their particular window. So for example, on this one here, we can see that the domain of this seems to go from about -12 to +12. So this is the notation we'd use, but we're going to be using this interval notation here, square brackets -12, comma 12, meaning the numbers between -12 and 12 inclusive. As far as the range of what you see, this starts at 0 and goes up to 12, so we would write it that way, and then using this interval notation is what we'll be using. So I'd like you to list the domain and range for the graph shown here. Press pause as needed, and then resume when you're ready. So look at the answers here. We already have the answers here. The domain for the green one is y equals absolute 2x. Domain is from -6 to 6 inclusive. The range is still the same as it was before. For y equals absolute 3x, the domain is only from -4 to 4 inclusive. Range is still from 0 to 12. And y equals absolute x, domain -3 to 3 inclusive, still the range is the same. Using the patterns that you're observing there, what would you expect the domain and range to be for the graph of y equals absolute 6x? Press pause, press resume when you're ready. Well, the domain would be from -2 to 2 inclusive. The range is still from 0 to 12 inclusive. How could we verify this? Well, I went ahead and graphed it for you, and you can see that y equals the absolute value 6x is going to go from -2 to 2 inclusive, and the range still from 0 to 12. So let's generalize our findings here. In the graph of y equals absolute of the quantity k times x, as k gets larger, the graph gets narrower. We can also say that the relative domain here gets smaller, while the range remains unchanged. Another way to word this is, in the graph of y equals absolute k times x, as k gets larger, the graph compresses in the horizontal direction. It compresses, seems to get smaller, narrower, while the range remains unchanged. Consider going in the other direction. If we go from here to the left as k gets smaller, the graph expands in the horizontal direction. And again, the range remains the same. How does the value of k affect the domain? Well, here when k is 2, the domain was half of what it was. When it was 3, it was a third of what it was. And when k is 4, it was a fourth of what it was. So generalizing, for any value of k, the domain seems to be 1 over k times what it was before. So we use the absolute value function. Would this hold true for other graphs of other functions? Let's investigate further. Let's look at the quadratic function, compare and contrast the same types of graphs here. Here we have the graph parent function y equals x squared, which will be in red, and we have the slider right here, so this is y equals the quantity of 1 times x squared. When I increase k to 2, you can see in blue what happens to the function. Quantity of 2x squared, quantity of 3x squared, and so on, compared to the parent function, which is in red. And when I go back down, you can see what's happening as we go back down. As the value of k increases, what did you notice happening to this graph? Once you've answered, resume. The shape of the parabola gets narrower as the value of k increases. As we did before, let's look at the graphs of these side by side. Y equals x squared, y equals the quantity of 2x squared, and I skipped 3 and went to y equals the quantity of 4x squared. And as we did before, we want you to list the domain and range of the graphs as they appear in this particular window. For example, what's the domain of this graph right here? Well, it looks like the x's go between -4 and 4 inclusive. We'll write it this way. And the range, the y values are from 0 to 16 inclusive, and we will write that again using this bracket notation here. So take a minute right now and list the domain and ranges for these, the green and the brown graph. Press pause and then resume when ready. So y equals f of 2x, which is the quantity of 2x squared. The domain is going from -2 to 2 inclusive. Range is the same. For y equals the quantity of 4x squared, domain only goes from -1 to 1 inclusive, and 0 to 16 again. Generalizing our findings as we did before, in the graph of y equals the quantity of k times x squared, as k gets larger, the graph gets, you guessed it, narrower, and the domain of this particular limited domain gets smaller, while the range remains unchanged. Another way to word this is, as k gets larger, the graph gets compressed in the horizontal direction. Range is unchanged. Going in the other direction, as we go from larger for k to smaller, the graph expands in the horizontal direction, gets wider in this case, as the range remains the same. How does the value of k affect the domain? Well, when k was 2, the domain was a half of what it was before. K is 4, the domain is a fourth of what it was. So for any value of k, the domain is 1 over k of what it was before. Our final example is going to look at a generic function that we're going to compare and contrast the graphs of these here. A function you probably have never seen before. I just created it. So this is the graph of y equals f of x. I just created out of a line, a semicircle, a horizontal segment, and another slanted segment. Okay. So right now the value of k is 1. So this is the graph of y equals f of x. Here's the graph of y equals f of 2x. compared to the graph of f of x, which is in red, the parent function. And as we increase k, again, notice what is happening to the graph. Again, let me back that up a little bit and see it again. So this is y equals f of x. In blue, y equals f of 2x, of 3x, 4x, and so on. As the value of k increases, what do we notice happening? F of the quantity k times x. Pause is needed. The shape of the f curve gets narrower as the value of k increases. Let's go ahead and look at those graphs side by side. Here's f of x, f of 2x, f of 3x, and f of 4x. And again, as the coefficient increases, what's happening to the graph? Getting narrower, as we said before. But let's go ahead and look at the domain and range of those graphs. So for this one, what would be the domain and range? Press pause as needed and then resume when you're ready. So the domain would be x goes from -12 to 12 inclusive, shown here. And the range goes from 2 to 10 inclusive. So I'd like you to go ahead and list the domain and range for the rest of these three here to compare to this one. Press pause and resume when you're ready. Looking at the solutions for f of 2x, y equals f of 2x, the domain is -6 to 6, range is the same. For the red one, domain -4 to 4 inclusive, range is the same. And for f of 4x, domain from -3 to 3, range is the same. Generalizing our findings, as k gets larger again of f of the quantity k times x, the graph gets narrower, or you can say the limited domain gets smaller, but the range remains unchanged. Another word to use is as k gets larger, the graph compresses in the horizontal direction. Going the other direction, if we go from 4 to 3 to 2 to 1 for the coefficient of x inside the f function, it expands in the horizontal direction, or gets wider in this case. How does the value of k affect the domain? When it was 2, it was half. 3 was a third. 4 was a fourth. So for any value k, the domain seems to be 1 over k times whatever it was before. So to summarize, if we look at f of equals f of the quantity k times x, where k is greater than 1, as k gets larger, increases, the graph compresses in the horizontal direction. And as k decreases, the graph expands in the horizontal direction. Here, in the first part, it gets narrower. Come back here, coming back the other direction, it gets wider. This concludes the video.